was here. Let's just go back a step. So I think what we said was if for wiring between the gates has a resistive component and a capacitive component, and that a pi model gives very good accuracy. And specifically a 3-segment pi model. And the pi was just, dividing things up into R, C, and C, and basically using 3 of those segments. And then we used this example where, where we had, when we were calculating, if you guys remember, when we were calculating the delay of gates, if we had a, let's say we had a 10x inverter, we had a R over 10 resistance, and let me actually do this. If we had when we were just looking at gates, if we had a 10x inverter driving a 2x inverter, we could replace the 10x with a R over 10 resistor, a switch, and the capacitor would be 10C. And there would be a capacitance of 20C for the P MOSFETs. And then this output would just go to the gate of the 2x, which would have the PMOS gates would be 4C, and the NMOS would be 2C. So if we just, with our simplified model, if we just had this circuit without any interconnect, we just end up with this, and we'd calculate either the pull down or the pull up, and we'd had R over 10, and we'd sum up all the capacitors and so on and get the sort of a RC time constant. Let me just move this over here. So this would be the model. Now, if we said if we had a an actual situation where, as in real life, you will have some length of wiring here. This would have an RC component. This guy would still look like here. Let me shrink it down a little bit. And on the receiver side, we'd have a similar thing. Oops, didn't like that. Come on, just grab that. Okay. And get rid of that. Size, there we go. And then we would, divide up this R and C into a bunch of three. I mean, we said three would be sufficient to give you um, pretty good accuracy compared to reality, and or let's call these R sub pi and C sub pi. Connect these guys up, and R sub pi's would look like they would look like R. Let's call this R total. R total divided by 3, and C sub pi's would look like C total over 6. Everybody with me? Any questions? So then basically the delay would be sort of adding the delay, just the same way you do it here. So delay 1 without interconnect, this is delay 2 including interconnect. And whether interconnect causes a significant delay or not just depends on the RC values or how much interconnect you have in between. And you can use the same methods that we used with the Elmore delay when we had a complicated circuit here. We could use the same thing with the interconnect to calculate the interconnect, even if we were, had another line and another inverter, and this would have its own R and C. We could basically end up with its own R and C, and then the Elmore delay would just be for the interconnect would be R1, C1. Let's say we want to figure it out to here, plus R1 plus R2, C2 plus, you guys remember that. So we use the same methodology basically with RCs and get the same thing. Okay, so basically interconnect very simply adds its own delay, and it depends on the R's and the C's, and both R and the C depend on the excuse me, depend on the geometry of your interconnect, like how you drew it, how you drew the line, which metal line or which interconnect line you used, and then which process you're in. That'll give you the resistance and capacitances for those lines. Okay, so that's all. Having an interconnect as a delay line. The second issue that interconnects bring that we don't normally have is, what if you had an inverter, same thing, let's say 10x driving and 2x, but you had a bus full of these guys. Okay, you had these guys running halfway across the chip, and you had a sizable capacitance, say that was coupling these two lines. So what you would get is potentially crosstalk. So let's say this guy was trying to drive this guy high, and this guy wasn't doing anything. This guy, depending on this capacitance, this guy, this top guy, could affect this bottom guy. Okay, and this is called crosstalk. And so it has an effect of two things. It can, let's say again, this guy was trying to be quiet. This has the effect of some noise. So when this transition happens, this guy would get like a glitch, potentially. And if this glitch is within the noise margin, going back to quite a few weeks ago, we talked about a lot of noise margin is good for logic circuits, and part of what that noise margin protects against is things like this. So even if you have crosstalk, if it's less than your noise margin, you're okay. It'll settle, etc. It'll cause a glitch. It might increase the power consumption a while because that glitch gets settled by the current through this guy. This guy will have to provide the current to settle that glitch. So that's an additional current that'll have to pump into And it increases the delay that just even this guy has, because it's also driving this capacitance. So there are consequences even if you don't completely flip the other line, but depending on these values, you have some level of protection. So let's look at those. Okay, so let's say that it that there are that the layers above and below. So like typically what happens is you have some layers here, you have some other layers here. Let's say they don't do anything. Okay, so that we can just assume these guys are the grounded to this layer, and these are also grounded, and we're only looking at this capacitance shifting. Okay, so how much you have in terms of the effect on your delay depends on what these lines are doing. Okay, if you have so let's say A and B are both, let's say A is switching from 0 to 1 and B is staying at 0. Okay, so you have a certain voltage going, so delta V on B, so what, in that case, what A sees, line A, is it sees C, all the C grounds plus C adjacent. So we're just looking at A transitioning, okay? Same thing if A is going from 1 to 0 and B is 0, same thing happens, is A sees C ground plus C adjacent, or vice versa. It's just as long as A is shifting but B is constant, you just sees that one C adjacent. But let's say A is transitioning from 0 to 1 and B is transitioning from 1 to 0. So in other words, you have in time, A is going from 0 to 1 and B is going from 1 to 0. Now, because they're going in different directions, it looks like you have twice the capacitance, okay, between these two lines. Or, another way to look at it is Q is equal to CV, okay? So the change in Q with time, okay, C dV dt, if they're trend, so this is I, this is current, C dV dt. If these guys, these two lines, A and B, are transitioning in opposite directions to each other, one way to look at it is you have to supply twice as much current to basically charge that capacitance between them to the correct value. And since you're limited by the current, by your own saturation current, that increases your delay. So maybe that's the best way to look at it. So again, if you just look at this table, okay, if B isn't doing anything, and A is doing a change of basically this delta V between A and B, or just VDD, you just see one adjacent capacitance and C ground. If B is switching in opposition with A, you see basically twice essentially the capacitance that you need to charge or discharge. Okay, and the nice case would be if A and B are both shifting in the same direction. then you don't see the adjacent capacitance at all, which is kind of nice. But basically it tells you that, you know, this adjacent, this interwire capacitance can actually cause additional delays and maybe significant additional delays depending on the condition of your bus. Okay, so that's one thing that crosstalk does. The second thing that crosstalk does is actually injecting noise into the adjacent lines. And the worst case scenario is a case where your victim node is floating. Okay, if it's floating, you just have this really capacitive divider equation. Okay, so if C adjacent, so again, that's the capacitance between two lines. Let's say this is the aggressor. That's the line that's changing, and this is your victim. And there's this C adjacent, and this is C ground. If C adjacent is equal to C ground, then you'll see a huge change in the victim because it'll end up to being 1/2 of VDD. So that's definitely going to be over your noise margin, or right at, you know, if you, even if you had the perfect in out, you know, 50% of VDD noise margin, you would end up with right at the edge. So it'd be a bad situation. So when you have a floating node, but essentially you do not want floating nodes. That's why, you know, when we looked at these pass transistors for latches, if you guys remember, in fact, we had our one of these in our test. When you store, this is why this is such a bad situation, right? You've stored a value of a 1 here, which is already, you know, not as good a 1 as you'd like. It's VDD. It's not VDD. It's VDD minus a V threshold. And it's floating now. As soon as clock goes low and you've stored your latch value here, this guy's floating. So if you had another line going by this thing, and this guy is susceptible to basically crosstalk in a really big way. You could easily drive that point to a complete zero almost immediately. So floating nodes are really, really dangerous for crosstalk. If you don't want them if you can, and 2, if you have them, you really, really want to shield them with like sort of a metal cage with a little mini, you know, sometimes in our analog circuits, we have to have floating nodes for sample and holds and other circuits. So we build these really, you know, tiny Faraday cages around those floating nodes with different metal layers, et cetera, to shield them from noise. Okay, so fortunately, in a more typical situation, like in a bus, both the lines, even the line that's not switching, so both the line that's the aggressor and the line that's not switching, they're essentially being driven. Because remember so here's the line that is, say, going from, this input is going from 1 to 0, and the output is going from 0 to 1. And you have an adjacent guy in your bus that is just staying at 0. Even though it's at 0 and doesn't change, this guy, the PMOS, is on. So there is a resistance holding this line to where it should be. So you have a situation where this resistance is this victim's resistance, is dampening this glitch or resetting the glitch, or pulling the line back to where you're looking at. And so that sort of crosstalk depends on the relative resistances of the aggressor and the victim, but you're in a much, much better situation because if remember that if this P MOSFET isn't, remember that when you're switching, you start your transistor that turns, let's say in this case, 1 to 0. So this PMOS is just turning on. It's starting in saturation, and then as it's pulling this node up, it's going into linear domain. Okay, so what happens is this PMOS is already in linear mode, and this guy, the aggressor, is going from saturation to linear. It means it has a higher resistance than this guy if they're the same size. That's great, because it essentially means you have your victim to dampen that noise quite a bit. So this is kind of an example of the kind of crosstalk that you get. So you have, in time, you have an aggressor that goes from 0 to VDD, and let's say the capacitance, the capacitance connecting the two nodes is the same as the capacitance of the victim to ground. Then the victim might actually go all the way up to 50% and stay there because there's nothing pulling that back to ground. But if the victim has a driver that's driving it, depending on the strength of the driver, it can basically take that glitch, dampen it, so you stay hopefully well within your noise margin, and then it's going to bring that line back to what it should be. So again, at least it doesn't flip the line, so in terms of this crosstalk, but because your victim has to basically charge this point back down, the N MOSFET here is working to keep this capacitance from going up and bringing it back down. You're actually creating a current condition to discharge this capacitance back down, which is adding to the power consumption. Okay, I think this is kind of saying, we get extra delay and extra power consumption. We haven't talked about dynamic logic yet, I don't think, but they're particularly susceptible. It's a type of logic. Hopefully we'll get to it sometime this semester, but it's intended to have, go faster and lower power, but it's really, very, very dependent on glitches. Okay. So that's about crosstalk. Now, as a designer, you have some ability to control some of these things, especially on long lines. Okay, so the best thing to do to control things is, I don't know if you're going to talk about that, but the first thing to do is actually in floor planning. You want to create a situation where, when you're figuring out where your different circuits are, so let's use, I don't know, circuit 1, circuit 2, whatever. You want to control at every level, both at gate level, at the block level, at all these kind of levels. You want to control where things are, so your interconnect is as physically small, the lines are as physically short as possible. That's job one. Okay, but let's say you've done all that and you still are running these lines. You have, especially when you're looking at buses, you have a few degrees of freedom. Okay, so one is you can, if you want, you can play with the width of the line by increasing the width. you have reduced the resistance and increased the capacitance. Resistance, the capacitance has this fringe component. So if you increase the width of the capacitance from the minimum, you are, for a while, you're reducing resistance faster than you're increasing capacitance because you have this extra fringe capacitance. But after a while, it doesn't really help you. And as you increase the width, you may be like reducing your crosstalk possibility. But again, you're sucking up area. Spacing, the further out you space components, you're reducing the adjacent capacitance, you're reducing the crosstalk. But again, you're sucking up area. The lower the layers you're in, the tighter things are with each other. So maybe you can shield lines from each other. You can do things like you can run, let's say here, if you're on metal 1 and you're on a tight pitch, you can run VDDs and grounds around your data lines. So these can shield the data lines from each other on the same line, metal line. Or you can go to up higher layers to reduce your actual resistance, possibly reduce your capacitance. And so anyway, it can also shield, as we talked about. By the way, one of the things I always thought back in the day, you could count on your upper layers. So, you had your lower layers and you had your upper layers. So you always thought, oh, great, my lower, if I want something that's lower capacitance, I go to these upper layers because, that's this capacitance to ground is lower. But that's no longer really the case. It's not guaranteed that, for example, a metal 3, assuming they're both not, adjacent to any other lines other than the substrate. There's no longer the case that necessarily metal 3 will have lower capacitance than metal 1, because if metal 1 looks like this, metal 3 may look like this, just the way it's constructed. And it might end up having a lot more fringe capacitance than metal 1. So again, it's no longer guaranteed that just because you're jumping up to higher level metals, you can reduce your capacitance. So it's just something to make sure you guys look out for. Okay, lastly, when you have, this is like a question that always comes up. Let's say you have a really, really long line. So something that goes a significant amount across the chip. Should you just drive it a single line, or do you break it up and put repeaters in between? So, I won't go through the derivation, but it ends up that if you have a really long line, the RC delay is dependent sort of in L squared, because R is dependent on L, proportional to L, and C is proportional to L. The longer it is, higher capacitance, higher the resistance. So the RC delay ends up being proportional to L squared. It turns out that if you go to sort of short segments, you end up, the RC delay of each one of those segments ends up more dependent on L. But then you incur a delay of these plus sort of N buffers and buffer delays. So this is done a lot. When you have a long line, you divide it up into smaller lines with these buffers thrown in, and the length of the lines, how many buffers you throw in, have to do with so there's an optimal point where the delay of the buffers isn't adding more than you saved by breaking up the lines. And you can take to get an exact closed equation, you take the derivative, etc. But you basically, the upshot is it is favorable to break long lines up and to put repeaters in between. And it turns out that these are sort of how it's calculated. You do pay in terms of energy, so power consumption, because you have added inverters, but you gain in speed. And this is kind of gives you a trade-off of where you might end up. And some of this, is assuming you have exact type of things. But the idea is that if with the right type of sizing, you don't have to give a huge penalty in extra power consumption, but you can get a significant improvement in the wire delay. Okay, so that's all I had for delay. Sorry, for wiring. Any questions? Just a huge topic, but that's where I'm trying to simplify it to this. Any questions so far on wires? If not, we're ready to go to our next topic, which is sequential circuit. Okay, so let's see. Get my notes out. Okay, so what are sequential circuits? So far, we've talked about so I want a thick line. No, it's too thick. So far, we've been talking about combinational circuits. Like, inverters, NAND gates, NOR gates. Basically, any circuit that its output depends on some combination of inputs. So, the output only cares about what's on its inputs now. It doesn't have any memory, doesn't remember what happened a picosecond ago, a nanosecond ago, whatever. It just, whatever is on the input, it'll make some decision on what's on the output. Now, sequential circuits are circuits that their output or their state, their output is dependent on input and a previous state. Okay, so what are examples of that? So examples of that are like finite state machines. Yeah. Like finite state machines like this guy. So what is a finite state machine? Well, it's kind of like, I think the best example I've heard of is like a vending machine. So if imagine if vending machine had no concept of what came before. You put your quarter in there, so it's okay. Now you press a button, but the machine doesn't remember that, only knows its present state. It doesn't remember that you put in a quarter in there. And then it doesn't know, like the next step is when it dispenses, let's say for some whatever reason, it dispenses your Diet Coke or whatever. It doesn't remember that it already dispensed that Diet Coke and not to give you another one. So anyway, vending machine is a good example because when you put your money in, it takes it from one state to another state. Now it makes it ready to, look at the buttons that you're pressing. You press the button and it goes to the next state where it, dispenses what you ordered. And then it goes to the next state where, again, it's like waiting for more money to come in. So that's an finite state machine. If you did not have an idea of your previous state, you couldn't have those kind of things running. Second good example is like a pipeline, like in your processors, where you are having you need a certain amount of functionality. So you're trying to do a certain functionality and you're breaking it up into steps that may be of different delays. Okay, and what's the benefit of a pipeline? Well, imagine if you didn't have a pipeline, you would have to feed so let's call this CL1, CL2. So let's say you had your input here and your output here. You would have to wait D1 plus D2 till you get your result. Okay, but if you put things in a pipeline, what happens is every sort of pipeline delay stage, the first time you fill your pipeline, you still have this sort of total delay. So in this case, you would end up with D plus D to get your first output. After that, as you keep filling your pipeline, you get a new value every D time. So basically you can get faster, you get more throughput, but you have to fill the pipeline. Okay, so that's my view of a pipeline. And so a pipeline also has the same thing. It needs to sort of have it needs to be able to tell the difference between this guy and this guy. So by putting these clock controlled stages or flip-flops or latches or whatever they are, is you've basically separated this from this, and now you can have a situation where you can pump stuff through this pipeline. Okay, and by the way, this as a aside, actually, this is a good time to talk about this. Yeah, that was a good time to talk about it. Any questions about sequential circuits, like the theory of them? Again, it's just something that puts kind of a timestamp on stuff is the way to look at it. Some people just think of it as a memory, and I think the book does a good job of saying how it's really not just a memory element, but it's a way to create time tokens, essentially. Okay, so that's at a very high level description of sequential circuits. Another thing that I'd like you to keep in mind from a high level is once you have these sequential circuits, you have something called a clock. So if you have sequential circuits, yeah, boy, I got really poor handwriting. It means clock. Okay, you can't have sequential circuits. You can't have time tokens if you don't have a clock. And think of a clock, okay? Think of a physical clock. You have your chip, and now you have, let's say, I don't know, we've been talking about 10, say 10 billion transistors or whatever. Lots of transistors. So, you might have millions, I don't know, hundreds of thousands of sequential circuits, whether, they're flip-flops or latches. We'll talk about both, but they all need this clock. So this is the one circuit that has to be, and these flip-flops, sequential circuits, whatever, are distributed all over your chip. So this is your chip. So this clock needs to be everywhere on this chip. Okay, so you got two really big problems. One is, when we were talking about power consumption, okay, we said clock is particularly a power hog because of our equation. Now, this is the one equation you have to remember now, CV squared F. So clock has two big problems. One is, by definition, it's the fastest, clock is the fastest switching thing. Clock is the fastest switching circuit or switching signal. So F is huge. So by definition, it's transitioning every clock cycle. So that's not helping you. And because you're driving all these flip-flops, you have a huge capacitance hanging off of this line. So that's problem or opportunity number one, challenge number one with clock. Okay, number two is the delay variation. Okay, so when I went to grad school, my thesis topic was to have an optical clock distribution across the chip. So, we had, anyways, it was pretty involved, but there was you're trying to control a laser source that would basically shine light into all these places, pulse light, all at the same time. So everything would get clock at the same time across your whole chip. But in real life, in an all electronic system, you have, your clock, and it might be going, sort of, this is one side of the chip, and then this is another side of the chip, and you have, I don't know, other capacitances and even higher capacitances, whatever it is, different delays. And these are all clocks going to different places in your chip. So these things are all getting to where they're getting at different times. And that delay variation is called clock skew. Okay, which is a very important thing. So a lot of your work in the design of a chip goes towards managing your clock. It goes towards creating your clock, distributing your clock, worrying about the power consumption, minimizing the power consumption of the clock, because all these sequential circuits need a clock. Okay, so just as, again, very high level view of clocks, and we'll get back to clock and all the issues we'll have with the clock. Okay, so I'm not going to talk about the pipeline, why we need pipeline. I'm assuming you guys all get why you need to put in things through a pipeline. And And when you, I mean, it's well, anyway, I won't talk about fiber optic circuits because that's its own thing. But um, long story short, in these kind of things, you don't need a clock, but you do need them in the circuits we talked about. So so another way to look at these sort of pipelines is we have these sequential circuits. So I'm just going to call all of them flip-flops because, as you'll find out, I don't like latches. So let's say you have a combinational circuit 1 and you have combinational circuit 2. Okay, so it could be that for whatever reason in your pipeline you have, it's not guaranteed, in fact it's almost 100% sure that you won't be able to delay through your combinational circuit stages to be exactly equal. There's just no way you're going to make the, these will each have potentially thousands of logic gates with different inputs shifting at different times. There's almost no way to make, D1 and D2 exactly equal. So one thing that this pipeline, these sequential stages are doing, I'll just draw the clock going to these guys. Is they are forcing basically this clock delay. They're forcing a maximum delay, a set delay in each one of these combinational circuits. Basically, if you had a combinational circuit that was very fast, it would have to sit there and wait for the slowest combinational circuit. So basically, taking us one step back, is your clock determines your minimum clock speed or maximum clock period, decides what the longest delay could be between stages. Okay, and basically everybody then has to wait for that delay to happen to get to the next stage. And this is called the clocking overhead. Okay, so basically the sort of the fastest circuits will have to sit there and wait for basically the slowest circuits to catch up, and the slowest circuits determine your fastest possible clock rate. Okay, so that's your so-called sequencing overhead, but you're stuck. Okay, so that's at the high level looking at sequential circuits and clocking. So now let's talk about the individual circuits. So generally you have two types of sequential circuits. Flip-flops that are edge triggered, put a smiley face, and latches that are edge triggered, which do not use, but we'll still have to talk about them, or use with enormous caution. Okay, so what's the difference? Well, a latch, is level sensitive to the clock. So it's level sensitive to clock level. And a flip-flop is edge sensitive, again, to the clock. Okay, so let's see what happens. So we have a latch here, and we have a flip-flop, we have a clock, and we have a D going to both, basically an input to going to both. So let's first see what happens at the latch output, which is here. Okay, so we said the latch is level sensitive. That means, let's, for example, say this latch is high level sensitive. So basically it'll pass anything that happens during this high transition to its output. So let's say the latch was, the Q value was too low to begin with, and D goes high. A certain time, there's some delay through the latch, but then after a certain amount of time, the latch would go high, the output would go high, then it would follow, and then when the D would go low, the output of the latch would go low. Okay, and it would basically follow D from here to here. So this is, I don't know, transparent latch. But here, whoops. Out here, notice the clock is no longer high. So the latch then in this period, the latch is, you could think latch is opaque. So doesn't matter what D does, D can do whatever it wants. Nothing happens on the latch output. But basically you'll follow, as long as the clock is high, you'll follow whatever your input does with a little bit of delay. Okay. If flip-flop is edge sensitive, means that it won't do, let's say it's rising edge sensitive. Okay, so it'll sit here, this first rising edge, while D didn't do anything in that rising edge. D can do whatever it wants, 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 because you don't get the next rising edge till here. Let me write this down in red. And then when you see your next rising edge, it'll look at D and go, oh, okay, D is high now, so now I'm going to go high. Okay, so that's the difference. Like if you give both latch and flip-flop the same clock and the same D input, this is, you'll get significantly different results, at least in this case. Okay, so one is level sensitive and the other one is edge sensitive. And it could be, either one could be high, or sorry, the latch could be high or low sensitive, level sensitive, depending on what polarity of clock you use. And a flip-flop could be either rising edge or falling edge sensitive, again, depending on your specifics. Okay, so now let's look at different, like sort of the evolution of the latch. Okay, so where it all started was with just a simple pass transistor. Back in the day, you just didn't have that many transistors in your chip, so you wanted to use as few as you could, so you just used the pass transistor. So it was good in some ways. The pros were it was really small. And then sort of low clock overhead, meaning that, i.e., clock only drives one gate. As we'll see, as these things get more complicated, you keep putting more pressure on the clock. But it has a lot of problems, okay? Problem number one, as you guys are familiar with the, somewhat familiar with this from the test and the project. So first thing is you get a VT drop. If you're trying to pass VDD through here, this point will get VDD minus the VT. Okay, it is so-called non-restoring, which means that once you have that, that's what you're storing. There's nothing in the circuit. There's no feedback loop. that makes this go back up to VDD. Okay. You can get so-called back driving. That means that there is, if you had some other kind of circuit, like say you had a sort of using this thing with another connection, this guy could back drive into this thing. Output is noise sensitive. We just got through talking about that. So the output is floating node. And that's very crosstalk sensitive. It's dynamic, which is another thing you guys looked at. So if what we saw in the lab, that if you had, let me actually draw the whole thing. So let's say we had the clock doing this and the data doing this. The Q value would do, I'm gonna sort of make it bigger, but it'll look familiar with you guys. It would go to sort of VDD minus V threshold. And then something that we haven't really talked about in this class, it's basically you get something called charge feed through, but again, you'll see that in your analog CMOS classes. And then you'll get discharge of Q, basically because of leakage. So basically, you can think of it as a dynamic circuit. You can't keep the value there statically. You'll have to periodically go there. You have to dynamically go back and recharge it. So that's because of leakage. And then finally, notice we are driving a source or a drain. We're driving a diffusion here, okay? And putting the value on another diffusion. Most of the time we've been driving just fully capacitive gates. So just driving a diffusion could have lots of problems. For example, if you somehow, for noise reasons, you had your low had a low going glitch that might be a few hundred millivolts below ground, which could happen because of power supply noise or other kind of crosstalk. You could have some serious problems because you're dealing with diffusion and not gates. You could actually dump charge or lose charge to the substrate. Okay, which has lots of issues. Okay, so this had lots of problems, but it was small. Okay, low clock overhead. So the next step was to make a transmission gate, and now you've got, whoops. By the way, guys, I know I'm talking a mile a minute here, but stop me if you've got questions. Okay, don't be shy. So here you got, clock and clock bar. So on the positive side, again, we're familiar with the transmission gate. We'd have no VT drop. But on the negative side, we need an extra clock or inverted clock. I just call it inverted clock. Need clock plus clock bar. So, another way to look at that is we have this extra gate capacitance that we're driving. So our clock network, which could be either clock or clock bar, has got more power consumption built into it. And then, it has almost the same issues though after that. If I was going to draw this guy's function in terms of clock and data and looking at Q, it looks a little bit better. Basically, it goes up to VDD completely. For again, reasons I won't go into, it'll have a much smaller pedestal for the clock feed through, but then it'll still leak, just like the other pass transistor latch. In fact, the leakage may be higher, because now you have more diffusions, another transistor hanging off of this thing, so leakage might be worse than pass transistor. So not great. Okay, so this is the next thing people came up with, was they stuck an inverter after the pass transistor, or they put the inverter before. Okay, so on the plus side, this is restoring. That means if this guy, is busy drooping, until a certain point, this node will stay. Let's say this guy's drooping, so it's going from VDD down. For a long time, this guy will stay at ground. It'll stay at the right logic value. And then all of a sudden, once you get past the value, it'll switch over. So it is restoring. There's no back driving, meaning that nothing can affect this value because this inverter is buffering it. Okay, and it's either fixing one of two problems. One of them is, either you have the inverter on the output, so you're shielding yourself from output noise, or you are not driving a diffusion. So whatever's driving you is driving a gate again, because you've shielded this diffusion, depending on whether you put your inverter on the output or the inverter on the input. Okay, on the minus side, somewhat, is that you have an inverted output. It's not the same as inverted polarity from your D input. Okay. So now we're talking how to get rid of this this bad dynamic latch. So let's take a look at this. This is what we did. So we have a first inverter stage. And we put in a second inverter stage. Notice that this guy is clock enabled. Okay, and we have this feedback loop. Okay, so all of these things together, so you have feedback, you have one inversion, you have another inversion. That all adds up to positive feedback, which normally is a really, really bad idea, because it makes your circuit locked up. If you were, trying to design an amplifier and you ended up with positive feedback, you would be screwed. And it's, something that happens, unfortunately, if you're not careful. But anyway, positive feedback is usually considered bad, except in things like latches, because what it's doing now is, let's say you started with a value of 0 here, you ended up with a 1 here. And this inverter is, because of that 1 on the input, it's reinforcing the 0, which again reinforces this 1. So this thing basically locks up once it latches. Okay. And the reason you have this enable on this inverter, that's an inverted version of this, is you want to make sure you break this feedback loop when your input is trying to drive this node. You don't want to be fighting with this feedback loop. So you momentarily break the feedback loop when you're writing to this node. And then once you disconnect your input, you reestablish the feedback loop, and it'll keep that as long as this feedback loop's going, as long as it has power and it's enabled, it'll keep that same value in there. So now you finally have a static latch. I'll keep the value there. There is, let's just say there's backdriving risk. If you're not careful about, these clocks, you could have momentarily this transmission gate on at the same time as the inverter that's feeding back, and you could be fighting on the input. But notice the other thing this doesn't have. This is not susceptible to leakage, because this node can, you can have as much leakage as you want on this. You are going against a on transistor that's driving you with orders of magnitude more current that you could leak off no matter how bad of a process you're in. So these kind of latches are now really essential, because your leakage is so high on new processes that it's really, really a bad idea. Well, sometimes people still do it, but very, very dangerous to have a dynamic latch. So these static latches are now, I would say, almost essential. There are always those cowboys who still use some dynamic latches. Okay, so now there are sort of improvements on this. Now, you can put a buffer on the input. So that gives you kind of a non-inverting output, because you have one inverter and you have your second inverter. So Q is not an inverted version of D, and you're driving now a gate. Okay, that's good. Then the other thing you can do is actually just use this feedback loop by itself and drive your outputs with another inverter. That way there's no chance that something else might disturb this feedback loop. So you got a very solid feedback. So this is a pretty solid design. Okay, there's no backdriving. So this is what's considered a fairly safe design, fairly robust design. But it's got some problems. Okay, you have one delay here because your inverter. There's some delay because of the pass transistor, and then you have another delay here. So it can be kind of slow from input to output. And now notice that your clock or clock bar, basically your clock network is driving 4 gates. Okay, you got this guy, this guy, this guy, and this guy that you need to drive. So a lot more loading on your latch. And you can kind of have variations of this, but I won't go into that. But okay, so brings us to the flip-flop, and guys, the flip-flop, at least my explanation of the flip-flop, should I do this now? Nah, I'll let you guys because my explanation of a flip flop is actually pretty involved, and I think flip flop is actually a lot more important for you guys to understand because my recommendation 99 times out of 100 is to use a flip flop and not to use a latch. Anyway, so I think I'll stop here and then we'll pick it up at the description of flip flop on Tuesday. Any questions?
Nope, no
Nope.
questions.
Okay, guys. Thanks. Have a good weekend.
Professor,
Yeah.
will you give us any example problems and when is the exam?
So I will give you guys homework problems this weekend. And I will also give you guys project 2 this weekend, unfortunately for you guys. So we'll have to have at least 2 projects. And then we have a couple of options. My suggestion is to have the final exam during finals week. Or, well, sorry, let me take a rewind. So we don't have a final exam, we have a second midterm. So we're only covering the material from the first midterm on. So that's sort of the first thing. So that second midterm either can come in the week before the finals, sort of like in our last class, or we could have it the regular time during finals week. Anybody have an objection to having it during finals week?
Not me.
Sounds good, thank you.
Professor, is it going to be like midterm 1 where we have like 24 hours to turn it in, or is it going to be in class?
Yeah, it'll be like midterm 1.
Okay, then final week sounds good.
Okay, sounds good. I mean, I'm also open because I know finals week you guys probably have a lot of tests. It's up to, if you guys won't have too hard of a time persuading me to get even a little bit more time. So, but anyway, we'll work that out as we get closer.
I think it would be best if we decide as we get closer to the end.
Yeah, I know you guys can kind of get a feel for what tests you guys got lined up.
Yeah, because some people might have a lot of finals on the finals week. That's why.
Yeah.
For project 2, how long will we have for that, and what do you think that will be covering?
So, what I'm going to have to make that project this weekend again, just because we don't have access to Cadence. So we got to kind of come up with projects that you guys can do with LT Spice. So what I think the project will be, let's see, where were we? No, it wasn't this one. Oh, I stopped the Zoom. But where was? No, shoot. Do you guys remember? I don't know. Maybe you guys can remember from the logical effort. There was, sort of the discussion started with this fictional character that was trying to optimally design a decoder for a register file. So basically, we're trying to design a decoder that would be driving a bunch of, I don't know how to describe it, I guess a bunch of register cells, a bunch of memory cells. So what I'm going to make, the project will be basically simulating the optimal value for that, basically like sort of calculating the optimal value using the logical effort. and then running the simulations to see how close you were essentially. I don't know if you guys remember that, but anyway, the decoders and a bunch of inverters and NAND gates and things. So nothing to worry
Yeah,
about.
I remember it.
Yeah.
Professor, from the last lecture on Tuesday, or this Tuesday, did you record that by any chance? Because I missed it and I was trying to look for like the video.
Sorry about that. I was too lazy to put it up. I will put it up tonight.
All right, thank you.
Sure. Okay, guys. Maybe I'm still showing this thing. So any other questions? Nope. Okay, guys. Have a good weekend.
Have a good one, Professor.
Take care.
Good
Bye.
Thanksgiving.